Now that we have all the control labels mapped out, we're almost to the point where we can start writing the microcode and make this computer actually compute things. But we still have one simple yet extremely important thing left to do: figure out the timing system. And for the simulation, it's really easy. In fact, this is all it is. Just a clock source and two labels, one of them is behind an inverter. This creates the two-phase system clock that makes everything work. But that's not what's really important. What's important is the theory of why this works, because without this, nothing would work. But why do we need two different clock phases to begin with? Well, this has to do with a topic we briefly discussed earlier about race conditions. A race condition is a conflict where the state of one gate is reliant on the state or timing of another. If this is left unmanaged, this can result in undefined behavior. If we have everything operate on a single clock signal, we'll run into issues where the registers or the RAM latch in data, possibly before that data is ready to be latched. For example, imagine if we want to add the value 5 into whatever value is currently in the ALU hold register. Well, the action of adding 5 means that the value 5 travels through the data bus into the input gates of the ALU. It then passes through the adder circuits, and then that value is presented to the ALU hold register. Those actions don't happen instantly, even in the simulator. If we take the simulator into step mode, we can see that the value takes several simulation cycles to propagate through the ALU. We can consider a simulation cycle to be the unit of time it takes to resolve a change in a gate. So if we have a buffer whose input changes to high, causing the output to change to high, we can say that this takes 2 simulation cycles to complete. One for the input and the other for the output. These delays are cumulative too, so a single buffer takes 2 simulation cycles to propagate the value, and adding another buffer to the output of the first gives a total of 4 simulation cycles, and so on and so forth. Let's say that the ALU takes 6 simulation cycles to pass an input from the data bus through the adders, but the hold register can latch a value in 2 cycles. If we had the ALU hold register latch at the same time that the value 5 was being presented to the ALU, the register would latch the value before the addition was complete. So the result of this will cause the ALU hold register to latch invalid data. This is a race condition. What we need to do is wait for the values to fully propagate through the ALU before we activate the hold register. One way to do that is to artificially delay the latch enable line by adding buffers. The propagation delay is cumulative, so this will cause the simulator to spend extra simulation cycles resolving these buffers, effectively acting like a delay in software. But this is not a good way to design things. It's too prone to making mistakes, and it becomes inflexible if we need to change things later on. And the calculations you do here to get the correct delay will not translate to the real hardware. Instead, what we can do is have an overarching clock signal for the computer, and this clock signal is split into 2 separate phases. The low clock phase is used to account for all the data propagation, and the high clock phase is used for latching the values into the memory, which includes the RAM and all the registers. This works because the system clock runs at a fraction of the speed of the simulator clock, so one clock cycle from our system clock happens over the course of hundreds or even thousands of simulation cycles, which is plenty of time for all our circuits to propagate their values fully. If we were to lay out the sequence of events from our adder example, we'd see here that all the signal propagation happens on the low cycle, so that the data is ready to be latched during the high cycle. At that point, the maximum theoretical clock speed is limited to the longest sequence of propagation delays in the computer. This is actually very close to how the real hardware works as well. In fact, for an earlier ancestor of this computer which used a 2-phase clock system, this is exactly how the system clock worked. But instead of the loosely defined simulation cycles, we're working with real units of time. The real logic gates within the computer operate over the course of nanoseconds. So a gate in Logisim which operates, say, over 2 simulation cycles, may in real hardware operate over about 20 nanoseconds. And there may be multiple gates that have to pass the signals one by one, each of which have their own propagation time that all add together. So we need to choose a system clock speed that allows us to fit a lot of small propagation delays under a single phase. We'll talk more about the timing stuff later on. The point to take away from this is that we're creating a timing system to account for the propagation delays of each circuit. For now, what we have are these 2 control labels. In the wiring menu, place down a clock and attach it directly to the high clock label. Then place an inverter, connect the inverter's input to the clock and the output of the inverter to the inverted label. Next, we just have to take care of the reset behavior for this computer. But that said, the concept of a reset barely applies to the simulated computer. The actual reset is mostly there to account for the unwanted analog behaviors in the physical chips. So instead what we'll do is we'll create a constant value of 1 and attach it to the npc clear control label for now. Now back at the instruction register module, the increment enable line will go directly to the high clock phase. The instruction register write enable will be qualified against the inverted clock phase using an OR gate. One input of the OR gate will go to the inverted clock phase. Then we'll create another control label named NIRWE and connect it to the OR gate's other input. Now copy this control label and attach it to position 2 of the third decoder. And here we are. This is the finished core of the computer, at least from a hardware perspective. We'll still need to add input and output devices, but we're a ways off from being able to use anything like that. Right now, we need to teach the computer how to actually do simple things like moving data around, but we can save that for the next part in the series, where we'll write our first microprogram.